Welcome. Today we look at the parametrization of curves. We have a time parameter which tells us what happens with a point in space or in two dimensions. So here I have a nice example of a pendulum. We see here I have this pendulum. I can run it and can see what happens. And at every time we have a position in this case, position on the sand. And I want to look at an example of such a curve related to this pendulum here. So what we have is x of t, y of t. So this is the example I'm going to look at, and t is the time parameter. Just time. And maybe let's take t goes from 0 to 2 pi. This is the parameter interval, and this is a curve. So this curve is a little bit challenging to draw. It produces curves like here on the sand, but usually you use a computer to draw this. But what happens when we are doing this by hand? So what we have to see, what happens at t equal to 0. At t equal to 0, this is at 1, 0. So we are here at 1, 0, t equal to 0. Now we can, when we increase time, the cosine t becomes smaller and the sine t becomes bigger. So this curve kind of moves somehow like that. Now, maybe at t equal to pi 6, we can still do that. At pi 6, then x is equal to 0. Then we are reaching here, and then at pi 6, this is just square root of 3/2 here. So we reach that point here at pi 6. T is equal to pi 6. Now if you look at t equal to pi 1/2, that's the next interesting point. Then the y is 0, so we have reached back here. And the cosine 3t is negative, so it will produce something like this. Not sure whether I can actually do that here. No, actually when t is equal to pi 1/2, this is 0 and this is 0. So this we somehow have to move somehow like this. So this is interesting. And what happens then next is we are turning around like this. Think something like that, and we might actually get here back to at t equal to pi. When t is equal to pi, we are at -1 here and here at 0. -1, 0. So that's -1 here. That is 1. So it's kind of like this curve. And then afterwards, it repeats again, but kind of just symmetric. So what happens is we probably get something like this. So we come back here. I'm not sure whether I got that right. Okay, let's look at a few examples. By the way, here in the meantime, you have seen this pendulum has traced an interesting curve. It's kind of like a Lissajous figure. Here there is also some friction, so the pendulum actually will settle down to an equilibrium. But let's look at an example here. Maybe one of the most important examples is cosine t, sine t. So let me draw here the curve, and so we have a cosine t. That's easier, because what happens here, we can also analyze this a little bit better using identities. For example, this is x and this is y. We find a relation between x and y, and so it starts again like before at 1, 0, but now it's easier to see what happens at pi 1/2. So t equal to 0 we are here, t equal to pi half we are here. So we have moved here, and then we at t equal to pi we are back here, t equal to 3 pi half, t equal to 2 pi we are back here. So t is equal to 2 pi we are back here. So it seems to trace a circle, and indeed we can see that x squared plus y squared is equal to 1, because cosine squared t plus sine squared t is equal to 1. So that's the parameterization of a circle. Very important example of a curve. And let's look at another example related to that. R of t is equal to t cosine t, t sine t. So in this case, it's still looks a little bit like a circle. But what happens here, the radius, we have seen polar coordinates the last time, this radius changes in time. So when t is equal to 0, the radius is equal to 0. So we start here t equal to 0 like that, and then the radius gets bigger and bigger, and it turns around like here, cosine t, sine t. So it's like r cosine t, r sine t, where r is equal to t, and this produces a beautiful curve here, and t is equal to 2 pi. We are here, t equal to 0, t equal to 2 pi would be back even further. 4 pi would be even further out. So this spirals out. So spiral, and this is a circle. Let's look at another example related to this Lissajous type, what we have seen the last time. Let's take cosine t sinus 2t. And in this case, this is a beautiful curve. It also starts at t equal to 0, we are here. But now cosine t becomes smaller, and at t equal to pi half, we are at 0, but also here at 0. So what happens is this curve has gone like that. So t equal to pi half, we are here. And then this becomes smaller than 0, and also here smaller. So this becomes something like that. And actually, what we see here, this is a nice figure 8. And by the way, just as a kind of a remark, this parameterization gives us a lot of information also about how we trace the curve. So let me just take here r of t is equal to cosine 2t and sinus 4t. I hope you see what happens. So in this case, we have just multiplied t here with 2, and this also with 2. So what happens is we just travel, with the same curve is traveled twice as fast as before. So it's the same curve. Same curve. Same curve here. But that is different parameterization. So the parameterization gives us much more information than just the curve itself. Let me take another example here. So this is A, B, C, D, E. Let's take R of t is equal to t sinus t. So maybe let's take t from minus pi to pi. We always usually give the parameter interval here. So we have here t smaller than 2 pi. At 2 pi we are back here. Also here we have taken t goes from 0 to 2 pi. Here also from 0 to 2 pi. Actually here when we go from 0 to 2 pi we trace it twice. We go twice around. Can also take pi. At pi we are already back here, equal to pi. So in this case, do you see what happens? So it's kind of always good if you write x and y. So you see y is actually just sinus of x. So this is a graph. Graph of a function which we know, the sine function. And so this is the curve. So this is plus pi here, this is minus pi, or minus 1 to 1. So this is a graph of a function. So if you want to draw a graph of a function, this is another way how we can draw a graph of a function. Let me just take another example here. R of t is equal to t plus 1, 2t plus 1, maybe 2t plus 4, so that we have a little bit more interesting curve here. This is x and y. I hope you see what happens here. We have looked at this type of curves before, and what we have here is actually, we can write this also as 1, 4 plus t times 1, 2. So what we have here is a line. So we have 1, 4, which is here. So we start here, and then we take a vector which is 1, 2. So 1, 2, which is going like that. And when we take that a t equal to minus 1, we go here through. So this line goes through here. So this whole curve here, this is a line. And what we have done here are all planar curves, curves in 2D. Everything we can also do in 3D. So the setup is exactly the same thing. So in 3D we have in 3D, let me just write it down here. So in 3D, what we have is r of t is equal to x of t, y of t, and z of t. So we have just 3 coordinates. And let me just take as an example g here. We take r of t is equal to cosine t, sinus t, and let's take t. Actually, maybe we have an example h also. So this is a beautiful curve, and so what happens here in this case, we have when we look from above, we have a circle, a cosine t, sine t, but then z just grows. And so what happens here is that we have a circle where so this is a spiral. Or actually helix, a helix curve. Let's look at another. I mean, in this case we also see that x squared plus y squared is equal to 1. So this curve actually lives on a cylinder. So this is a cylinder here, and this curve lives on a cylinder here, but it climbs up that cylinder. Let's look at the last example here. We take r of t is equal to t cosine t, t sine t, and t. So it's kind of a mix a little bit between what we have seen here and between what we have seen here. So this is interesting because we can also see a relation between x and y and z. What we see that is x squared plus y squared. What is x squared plus y squared? X squared plus y squared gives us t squared cosine squared t plus t squared sine squared t. That's just t squared. That's z squared. That's equal to z squared. So this curve lives on a cone, and let me just draw it here on a cone. So, and it climbs up that cone. So that's our last example. Okay, now we start calculus. We take derivatives and we integrate, and it's an old problem which the Greeks already have pondered. We are moving, this is a curve, just write this down, this is a curve here, r of t, parametrized curve, and we just write x of t, y of t, z of t. Now, let's just draw vectors. So maybe this is r of t here. And that's the origin. And then we have also another later time, r of t, t plus h. H is a small time later. And what we are interested in is the difference of this. This is r of t, this is r of t plus h. And what we can take is we can take the difference. Let me just make this green here. So this vector here, bottom vector, this vector is r of t plus h minus r of t. Of course, this vector rt plus h minus r of t goes to 0 as t goes to 0. So as closer we are getting, as smaller we are making t, as smaller this vector, this green vector rt plus h minus rt becomes. But what we can do is we can scale this. We can say, okay, this is the displacement rt plus h minus r of t over h. And so this is the displacement over the time which we have done. And this has a chance to have a limit. So when we look at that and then we take the limit, this is what the Greeks didn't kind of get yet, because they lacked just the concept of limit. And we'll come to Zeno, who was actually pondering this problem. And then what we get is, so when we take the limit, h goes to 0, r t plus h minus r of t over h. So you see that's kind of just x of t plus h minus x of t over h. And so this is what we call, so what we have is kind of, let me just write it down. So x of t plus h minus x of t over h, y of t plus h minus y of t over h, and z of t plus h minus c of t over h. I hope one can read this still, but you know what happens in calculus, right? These limits actually exist here. So this is, or if the functions are nice, this is called x prime t, y prime t, and z prime t. And we just write r prime of t. So r prime of t, this is this vector x prime of t, y prime of t, z prime of t, is called the velocity. The curve at t. So this x prime t stands for d over dt so that's a notation of Leibniz. Newton used this notation x prime of x dot of t. This is Newton. And this is Leibniz. So this is just more convenient to write O as prime instead of like f prime for the function derivative. But that's actually quite an interesting step here, and that's what the Greek philosopher Zeno of Elea, 450 BC, so that's already, so Zeno has pondered this question. And if he has pondered this question, so you have an arrow moving, and at every moment of time the arrow is at this fixed position. So how can it move if at every moment of time it is at the fixed position? So let me just illustrate this kind of what Zeno had in mind here. So this is a stroboscope here, which kind of tells us kind of at every moment of time this arrow is at a specific position here. And so the stroboscope tells you what happens at the time. So at every moment of time it doesn't move, right? So how can it move if it... So this is a puzzle which then only with the development of calculus has been solved. Okay, so here's an example of a curve. We have already seen this curve. It's a spiral. And we have the notion of a derivative r prime of t. So what we do is we just take the derivative of each part here. So this is minus sinus t cosine t 1. And this is tangent to the curve. So if we compute the velocity at this point here, this vector r prime of t is tangent. Now we didn't define what tangent means, but we can actually define it like that. That's what it means to be tangent. Vector becomes more and more in the limit, it becomes r prime of t. So this is the velocity vector. This is tangent to the curve. So this is the velocity. So we can compute this at any time t. So this vector here is like that. So at every time we have a velocity vector. Now we can also differentiate more. So the second derivative is very important still. So this is minus cosine t minus sinus t 0. This is called the acceleration. So in this case, this acceleration is minus cosine t minus sinus t t. This kind of pulls this is like a force. Think about it as a force. So m times the acceleration. So that's Newton. One of the reasons why this is so important is because of Newton's law, which tells that mass times acceleration is equal to force. But in this case, it's a vector going in like that. So this is r2 prime. So the acceleration in general doesn't have, can have any relation with the velocity. For example, if you're on a straight line, then the acceleration is parallel to r prime. Here it is kind of almost perpendicular to r prime. You can see here when you take the dot product here. It's actually perpendicular when you take the dot product. It is 0. And then we have higher derivatives. So r3 prime t. So this is called the jerk. And then we have the r4 prime t. Crack. r5 times of t. Snapple. And the pop. And they're not so important anymore because of Newton's law. Newton's law is really kind of tells us. But still engineers are looking at these higher derivatives. So you all know when we reverse the differentiation process, we get integration. And that's very useful. For example, if we know that the velocity, is equal to cosine t sine t. And maybe we know also the initial position. Maybe at r of 0, we are at the point 3, 4. Now we can compute r of t. So this is a problem. And we all know how to do that. In single variable, we know if we have the derivative given, we can find the function by just integration. And so what we do is we just we can write r of t. We don't care that there are 2 components or 3 components or whatever. We just write the same thing we would have done also in single variable calculus. We kind of integrate from 0 to t, and then we have r prime s ds. So this is now a vector, so it gives us a vector back. And you have to be careful also about that at t equal to 0 that we are at the right time. At t equal to 0, this whole thing is equal to 0. So we have to add here plus r of 0. So now it works, because at r of 0, that is 0, and that gives us the right position. So let's compute that. So we integrate from 0 to t. We have a cosine t, sine t, s. I have to use s. It's not good to use reuse the letter t has already been used here. The variable t has already been used, ds, and then plus we have 3, 4. So let's just compute that. So that's when we integrate cosine t, we get sinus. So we get sinus t minus sinus of 0. And here when we integrate, we get minus cosine t, and then plus cosine 0. And then plus 3. So in this case, that's actually just cosine. This is 1 here. So this is actually, so the result is r of t is equal to sinus t plus 3. And here we get minus cosine t plus 3, 2. Actually plus 5. So that's the solution. So there's a little bit a simpler way than just kind of going through this here. What you can do is you just take the antiderivative and then you fix the constants. So in this case, you can now check at t equal to 0, we are at 3 here, and at t equal to 0, we are at 4. So this works at t equal to 0. Cool. So that's an important thing. We can get from the velocity, get back the position. Okay, now even more important than integrating up the velocity to get position is integrating up the acceleration to position. So that's what is, let me just write that down in general. So if r2 prime t is given, and so that's actually a force. You have seen Newton tells us mass times acceleration is force. So that's often given. The force on a particle is given. And then we have given also r of 0 and r prime of 0 are given. The problem is find r of t. Now it's no problem. We can do that in the same way like before. We can just integrate twice. Just integrate twice. So what we do is, let me just write it down in general and then we solve a problem. So we have r prime of t. So that's the integral from 0 to t r2 prime of s ds plus r prime of 0. And then we have, once we have r prime of t, we can say r of t is equal to the integral from 0 to t r prime of s ds plus r of 0. So it's 2 stages. And it's exactly the same thing. Maybe I just don't make a general example in class, but we are looking directly at the problem called the free fall problem. Okay, a very special case is when we have a constant acceleration, and that produces us free fall problems. So let me just write it here because I will make a problem here, work out a problem here. So a special case. So if r2 prime t is 0, 0, maybe I write just directly minus 10. So this is the gravitational constant on Earth, almost 10. And so this produces free fall. So this is a gravity. So what we have is a problem like this, where the force is pulling us down with constant force. And so we have a, for example, an arrow or a ball moving here. So we are moving here, and so this is r of t. So we want to understand this trajectory of that of this ball. So why don't we take a concrete example here? So a concrete example. So problem. Maybe Roger Federer is shooting a ball, and so let's take this example here. So what we have is this is the x-axis, this is the z-axis, And y would also be there, but let's assume just y is equal to, so maybe y is equal to, is here. And then we have at a specific height, maybe, so we have maybe 6 here. At the beginning, we are at the beginning, so or maybe r of 0 is equal to 0, 0, 6. And we have a force, which is this gravity, which is given. R2 prime is given, and then we have also we throw the ball. We throw the ball with an initial velocity, which is given here. So maybe the initial velocity is equal to maybe 100, 0, 10. So that's the initial velocity of the ball, and maybe a tennis ball. And we want to know when does this ball hit the ground. So our prime of 0 is equal to, actually we write it as vectors. So this is also a point, but let's just write it as a vector. This is our initial vector here, 0, 0, 6. And our prime of 0 is equal to 100, 0, 10. And we have r2 prime of t is constant 0, 0, minus 10. And then the problem is find r of t. Find the trajectory, and especially find where does it hit the ground. Where does r of t hit z equal to 0? So that's a typical problem. Problem of trajectory. We know the ball will do something like that, and what we want to know is where does it hit the ground. It's an artillery problem if you are shooting rockets or bullets, and so this is a nice problem. So what we do in order to solve this problem, we are just taking the acceleration which I have here, and let me just do it here. I hope one can see this. Maybe one cannot see this here. Actually, maybe write it here. So this is the problem here. And what we do is we just start with r prime of t, r2 prime of t. We just write that down, which is 0, 0, minus 10. Now we take this r2 prime of t and we integrate. So we get r prime of t, we just integrate, we get 0, 0, minus 10t, and then we have to add the initial velocity plus 100, 0, 10. So plus 100 plus 0 plus 10. So this is our velocity, and we can double check this velocity at t equal to 0 gives us really this. So this matches with this initial velocity. So this is r prime of 0. Initial velocity works here, and now we can integrate this again. So we have r of t is equal to 100t, 0, and 5t squared. We just integrate that, and then we have to add up also r of 0. At t equal to 0, this is 0, so we have just plus 6. So we see that the solution to that problem is r of t is equal to 100t, 0, and 6, oh, minus 5. I forgot the minus sign, minus 5t squared. And now we can figure out where this is equal to 0. So this is equal to 0 for t. T is equal to square root of 6/5. This gives us the t, this gives us the, this is then z is equal to 0. And now we can figure out where this actually hits the ground. R of square root of 6/5 is equal to 100 square root of 6/5, 0, 0. So that's the point which we were looking for. 100 times square root of 6 over 5. That's the x value. The y value has not changed because we are not shooting in the... We have not given any y velocity here. And it's interesting, the curve here, this curve is a, see, quadratic. Essentially you see kind of when we look at that, this is a quadratic expression, and this is just a parabola. So when you throw a ball, or you throw an object like this chalk, this will follow a parabola.